we're going to start on resultant force for today, okay? So, real quick recall. So, what we end up having to recall is this little idea of a unit circle, okay? So, we're going to recall the idea of a unit circle. And let me kind of draw this out here. So we're going to call that our unit circle. So here's one up here, -1 here, and -1 over there. Now, if you can recall, like usually whenever we would do unit circle, we'd be given an angle. So here's theta, right? So here's our theta. We'll call this our z value. Okay. And I'm going to drop a line straight down, and this line across we'll call it x, and this line here we're going to call it y. Okay, I'll kind of zoom in for us here so you can see it. So x is the measurement from the origin to where the dotted green line hits. Okay, so you could say it's like from here to here. Okay, and y will be from there to there. So here's the thing. So since we know about this unit circle, then we can actually define stuff. Okay, we know that cosine of theta would be x over z, and we know that sine of theta would be y over z. Okay, now if I solve for x and y, I get that x is equal to z cosine theta, and y is equal to z sine theta. All right, but if this is a unit circle, then what is z? What's the value of z? 1, right? Because that's the radius of a unit circle, right? So since z equals 1, okay, then we actually get that x must be cosine of theta and y must be sine of theta, right? So I can make a vector u and call it components x, y, right? I can call it cosine theta, sine theta. Okay, so I can create a vector u, and I'm going to make the components x comma y, or cosine theta, sine theta. Okay, so just so you know, that u would be, that's our point, okay, x, y. All right, so we're saying basically that's our u vector. Now, according to linear combinations, I can rewrite vector u as cosine of theta I plus sine of theta j. Now this would result in a unit vector. Okay, so I'm just going to put right here, this is a unit vector, but we don't really want to do that. Okay, and I know it's a unit vector because we use the fact that z equals 1, right? So we know that the magnitude of it would be a 1. But what if I wanted to find any kind of vector, not just a unit vector, but a vector with whatever type of magnitude, okay? So what we do is we kind of leave out the unit vector idea, and what we're going to do is rewrite it like this. It's the magnitude of u cosine theta I plus the magnitude of u sine of theta j. Now this is called the resultant vector. Okay, this is the resultant vector. In other words, if you wanted to draw the vector with its magnitude and direction, you would do this. You would have to figure this information out. So resultant vector has magnitude and direction. Okay, the direction is in the theta, right? So once you know the theta, you can find the cosine and sine values and plug that stuff in. So it will give you your magnitude and direction. So that's our resultant vector. Sometimes they'll call that our acceleration vector or our velocity vector, just kind of depending on what's happening. But if they want you to develop a vector based on a derivative, then you call it the velocity vector. If it's its second derivative, you can call it the acceleration vector, whatever it happens to be. So if I can, because let me just double check here. Time for us ends at 42, right? So I'll try to see if I can just do one of these, or maybe I can get the second one. The last one for sure will take more time on it. But let's try at least get one of these in. So example number 5, maybe we'll just do the one for today. So the vector v has a length of 3. Now this is supposed to be an easy one, okay? So it has a length of 3 units and makes an angle of 30 degrees. Makes an angle of 30 degrees with the positive x-axis. So they want us to write V as a linear combination. Kind of underline that right here. So write V as a linear combination of the unit vectors I and j. And this kind of sounds weird at the very end, but they're basically just saying write a linear combination. A linear combination includes the i's and j's, but they're just saying, like, don't forget that it includes it, right? So they're just saying make sure you have that in there. I'll just give you a couple seconds just to finish writing that down. So the vector v has a length of 3 units and makes an angle of 30 degrees with the positive x-axis. Write v as a linear combination of the unit vectors I and j. So start off with the definition of the resultant force. Okay, so this is what they're wanting. Okay, they want to know the magnitude and direction of it. So I'm going to write this just to start us off. Okay, now like I said, this is an easier problem because of the fact that they're not making us do a lot of work. It's not a word problem where we got to figure out, how do these things combine together. So the magnitude they gave me, they told me that it has a length of 3. Okay, and they also told me that I have a 30-degree angle. So that means that this vector is 3 times cosine of 30 degrees I plus 3, bless you, times sine of 30 degrees j. All right, so we know cosine of 30. Cosine of 30 degrees is radical 3 over 2, so we're going to put radical 3 over 2 I. And then we know that sine of 30 is half. And then just combine your information. So v is equal to 3 radical 3 over 2I plus 3 over 2j. And this is what they want you to find. Nine minutes. Maybe, maybe not. We'll see. Maybe what I'll do is I'll write the problem and I'm going to draw the next example, and tomorrow we'll start it, okay? But today we'll write the problem and just draw the picture. But I mean, as you can see, this process is not meant to be hard. Now, of course, they can make it more difficult by putting in a word problem, right? And giving you situations where you got to try to figure out, like, how am I going to combine this vector with that vector, okay? But you probably have done that in trig. I'm sure you guys remember we did a little bit of that in trig. If not, you've done it in physics. If you haven't done physics, then you only did it in trig for a little while, with resultant forces and magnitude and stuff like that. If you're wondering, like, when the heck did we do it in trig? Do you guys remember doing pulley problems where things were hanging from pulleys with weights? So there was like little, like, triangular things, and then there was a weight down here, and it was hanging, and there was a downward force, and there were angles here you had to figure out and stuff like that. I mean, that was a long time ago, but that's kind of where you saw this in trig. So, all right, so let me give you guys example 6. Like I said, we are not going to do the problem, but we will write it down, okay? So 2 tugboats are pushing an ocean liner. So pushing an ocean liner. Each boat is exerting a force of 400 pounds. Okay, so each boat is exerting a force of 400 pounds. What is the resultant force of the ocean liner? Now, the way this question is labeled right now, there's no way you can do this problem, because we're missing angles, we're missing, like, what's going on with these tugboats. Are they pushing straight? So we are going to need a picture. Okay, so I'll do that really quick. A tugboat. So have you ever seen, like, when you have these big old ships, and sometimes they got to get these ships to move sideways out of a dock. They can't just drive straight. Now, some boats actually have the capability to put their engine sideways so they can actually push off. But tugboats are these smaller boats that have a whole bunch of power, and they get to the side you're trying to push over, and the tugboats almost have like these, like, bumper boat looking things in the front, and they just go up to the ship and then gun it, and they start to push the ship away. So yeah, they're like little boats that kind of guide ships in and out of harbor sometimes. So, but yeah, there are some ships that don't need that stuff anymore. They have little side propellants with air they could push sideways and stuff like that. So I guess it just depends on how nice the boat is. All right, so let's draw a boat here. Hopefully it's decent. So let's see. So we'll give it some smokestacks here. And for I guess we could put this little thing here. This is to indicate that it's a Carnival Cruise Line, because they seem to be the ones that do that. And we'll only put 8 safety or life rafts like the Titanic. I don't know what they were thinking. It's funny when you start, just when you think you're better than nature, nature says, no, you're not. All right? The unsinkable ship. So here we go. Tugboats, little tugboats. Okay, so they're going to look like fingernails almost. All right, and let me give it some measurements here. All right, so we know the force for force 1 is 400 pounds, they said. we'll put this one force 2 as 400 pounds as well. Maybe I should have put that near the bottom, because I'm just noticing I got to draw this out really quick right here. So this would be a negative 20 degrees. I guess I could do it the other way. Hold on. Should have planned this a little better. So this is positive 20 degrees. So we'll put force 2 is 400 pounds. Force 1 is 400 pounds. Let's see, is there anything else I got to label there? No, that's basically it. So that's the setup to the problem. Just before we finish off here, notice the angles that these tugboats are pushing in. One is a negative 200, one is a negative 20 degrees, one is a positive 20 degrees. So which direction should the big boat move? It should just go straight right? If assuming that there's no craziness to the water movement, which obviously there is, but in a perfect world, if they're pushing in completely opposite directions that cancel out, then that means that this boat should only move in a horizontal motion to the right. Okay, so tomorrow we'll start this problem off, and then we'll do another example.